Hello everyone, I'm Yonghee Kim, and today I will present CRIS, the power of imagination in hybrid verification. The main motivation for this work is hybrid verification, so let me begin by explaining what that means. Before we get to hybrid verification, let me first recall the standard program logic. Here, each component is verified against a logical specification typically given by pre and post conditions. In separation logic, these specifications also describe ownership of resources. This allows us to reason locally about one component at a time without tracking the whole program state. But there's a limitation, as adequacy theorem gives us a safety guarantee only when every program component has been verified. So I will call this full verification. But there's another approach. Even if we verify only some of the components, we can still get a formal guarantee about the whole program. This guarantee takes the form of contextual refinement between a concrete implementation and an abstract model. It says that the implementation's behavior always refines the abstract models under any identical context. In this picture, we set the context to be an unverified application. And that gives us a formal guarantee relating the source and target side. Concretely, the behavior of the implementation linked with application refines that of the abstract model linked with the same application. And frameworks like CCR, Simul-Iris, and Rhee support this kind of reasoning in the style of separation logic. Then we can apply lighter weight methods to the abstract program, things like model checking or testing. And because its state space is much smaller than the implementations, model checking or testing gets a lot more efficient. This is what we call hybrid verification. However, these frameworks share one important limitation. Their specifications are restricted to pre and post conditions. To see why that's the limitation, let me show you a motivating example. On the left side, there's a simple library called cell. There's one private variable, CV, that holds a value, and two functions that update or read it. The set function takes a callback CB as its argument, calls it, and stores the callback's return value in the private variable. Note that these gray box components will not be formally verified. They will be tested or model checked later instead. And the get function just returns the current value. So how do we specify this library using pre and post conditions? Let's see the get function first. Here, cell X is an ownership predicate. It represents exclusive ownership of the cell, indicates that the current value is X. The precondition requires the caller to provide this ownership before calling get, and the postcondition guarantees that get returns the current value, so R equals X, and it gives the ownership back unchanged, and that's cell X again. So together, the pre and post conditions precisely capture the get's behavior. For set, we can write something simple like this. The precondition requires ownership of the cell with some value X, and the post condition gives ownership back, but now with an arbitrary value Y. This captures the set may change the cell, but it loses the information that the new value Y came from the callback. So normally, we would recover that by assuming parametric pre and post condition for the callback, but the callback stays unverified here, so that assumptions will never be discharged, and with no discharge, there's no formal guarantee follows. To address this limitation, we introduced a new notion of specification, which we call imaginary specification, and a proof system that supports them called CRIS. The key idea of imaginary specification is that they can freely mix program code with separation logic assertions. To see this clearly, let's revisit the earlier example. First, we translate the pre and post conditions of get into an imaginary specification. It takes an arbitrary integer x, assume ownership of a cell holding x, and then guarantees the same ownership back. And finally, it returns x. Note that the red part encodes the precondition and the blue part encodes the postcondition. For set, in similar, takes an arbitrary integer x and assume ownership of a cell holding x. Then it calls the unverified callback, obtains a result I, and guarantees ownership of the cell now updated to I. Here's an important point. Unlike pre and post conditions, an imaginary specification can contain executable code like the callback invocation in the spec of set. Moreover, separation logic's assertions may depend on that executable code, as they do here in set, and the code can also depend on the assertions vice versa. To see how such imaginary specifications are used, let's look at the complete example. The program has three parts. The cell library from before is client main, and an arbitrary extra module foo. As before, unverified components are in gray. The main function first calls cell.set with its callback. Then it calls foo, reads the cell's private value with cell.get, and prints the result. We want to abstract this into a program like that. Directly calls the main callback and calls foo, and finally prints the callback's result. Now there's a subtle point in this refinement. At first glance, it might look invalid. So foo can override the cell's private variable by calling cell.set, and in that case, the implementation prints the result of foo's callback, while the abstract program prints the result of main's callback. But the refinement still holds. Here's why. The cell library is absent from the abstract program, so if foo tries to call it, that's undefined behavior on the abstract side, and undefined behavior makes the refinement vacuously true in that case. So the refinement holds even in this case, and I will now show how CRIS establishes it using only separation logic style local reasoning. The first step is to verify the cell library against its imaginary specification using only module local reasoning. In CRIS, we can establish this contextual refinement through separation logic style reasoning fully in iris proof mode. I'll skip the details here and focus instead on the more interesting part, verifying the client. So let's now look at the proof for the main module. We first give main an imaginary specification by simply adding assume cell 0 at the start of its main function. And our goal is to prove a refinement between these two programs using the imaginary specifications of the cell library. With the same cell spec linked on both sides, we prove that main's implementation refines its imaginary specifications. And only its implementation calls cell, so I will hide the cell on the abstract side just to make room on the slide. And again, this simulation proof is also carried out in iris proof mode. Now let's walk through it. We first take a step on the source side and acquire the resource cell 0. That just says the initial value in cell is 0. On the target side, we now have to call set. And because an imaginary specification is itself written as code, we can inline it and run it inside the simulation proof. First, we execute take. If it was on the source side, it gives an arbitrary value, but here it runs on the target side, where it plays a dual role. So we get to choose any value we want, and here we choose 0. And assume cell 0 also plays the dual role. It now releases the cell 0. More precisely, cell 0 is removed from the resources we own. Both sides have reached the same callback. So we run the callback on the both sides at once. When the same function is called with the same argument on both sides, our simulation rules let us jump straight to the continuation and gives both calls the same arbitrary return value, and let's call it R. Running the guarantee operation, we acquire cell R, and then we return to main. Next, both sides call foo at the same time. As with the callback, we jump to the continuation point. Here, we have important point to note. First, by the frame rule of the separation logic, we keep ownership of cell R across the call. This tells us that the value in cell stays unchanged, so we only need to reason about the case where foo does not change it. And what if foo does change it by calling cell.set? Then the encoding of the imaginary specification triggers undefined behavior on the source side, and that makes the refinement hold vacuously. Next, we run this imaginary spec of cell.get following essentially the same pattern. We choose the current value R, release R, immediately acquire the same resource back, and return R. So in the end, both sides print the same value R, and the simulation proof is complete. And we now have two separate verification result, one for the cell and one for the main. Let's see how they compose. First, we have a contextual refinement from the implementation of cell to its imaginary specification. Here we place main's implementation around this refinement as a context. And then we have also proved a second result, that main's implementation refines the abstract version of it when it's linked with the cell specification. And by transitivity, we get this contextual refinement. Then we can place an arbitrary full module around it as a context. At this point, we can also remove the cell library. This is always a sound refinement because any call to cell will trigger undefined behavior on the source side. And after one more application of transitivity, the only step left is to eliminate the initial assume in main. And this happens automatically through the cancellation theorem we provide. In general, that theorem removes the initial assume along with every matching pair of assume and guarantee. In this example, however, there's no such matching pairs, so the theorem just removes the initial assume and gives us the final top-level abstract program. Now let's take a closer look at the reasoning principles. Here are the simulation rules for the 4 key operators. The rules in the first row apply to the source side, and we use them when verifying with imaginary specification. And everything is dual, I'm sorry. We use that for against imaginary specifications. Take and choose introduce universal and existential quantifier. Assume and guarantee introduce magic wand and separating conjunction in separation logic. The rules in the second row now apply to the target side, and we use them when verifying with imaginary specifications. And everything is dual from the before. Take and choose now introduce existential and universal quantifiers. Assume and guarantee introduce separating conjunction and magic wand. So as you can see, there's a duality between the source and target rules. And there's a second duality here too, coming from dual nondeterminism. The blue operations use demonic nondeterminism, the usual kind, which you can think of as a union of behaviors. And the red operations use angelic nondeterminism, the dual kind, with an intersection of behaviors. Take and choose are the basic choice operators for those two forms, and the assume and guarantee are encoded using take and choose respectively. On top of these, we had inlining rules, and that let us inline a function call with a body of the function. These are the key rules that let clients actually use the imaginary specifications. And now, one credit to note here, the core idea of using dual nondeterminism to operationally encode separation logic assertion comes from earlier work CCR. But CCR does not have imaginary specification in their mind, and in particular, the inlining rules are unsound in CCR. Supporting inlining of imaginary specifications turned out to be our main technical challenge, and how we solved it is in the paper. In summary, the main novelty of CRIS is the notion of imaginary specifications. Traditional pre- and post-condition style specification describe verified components through logical assertions only. Imaginary specifications go further. They can freely combine those assertions with arbitrary executable code. And that's what makes them especially useful for hybrid verification, where some components are intentionally left unverified. And the overall structure of CRIS proof looks like this. We start with the implementation components separately and verify each one on its own, then build up step by step to an abstraction of the whole program. The imaginary specifications are the intermediate layers that let us do this. The two programs in orange at each end of the proof are the real programs. They are ordinary executable programs with no take, assume, or guarantee operations. And what CRIS gives us in the end is the refinement between those two orange programs. And that's the result does not mention any of the imaginary specifications in between. So how we define the gray ones, the imaginary specs, is not part of the trust base. Here's a loose analogy. Imaginary specifications are a bit like an imaginary number in math. Look at the example on the right. To prove the two real numbers are equal, we break it into 3 simpler steps that pass through imaginary numbers. The left side works the same way. We break the end-to-end refinement of real programs into several simpler ones through imaginary specifications. And we know of various follow-up works. Some are completed and some are in progress. Completed ones include supporting weak memory concurrency in CRIS, and together with prophecy and helping principles, building distributed systems with consensus protocols, and full support for C-Lite with assembly and linking through COMSET-M to get end-to-end verification. Support for impredicative higher order predicates without step indexing. Work in progress includes porting to Lean, which is mostly being done by AI, and liveness reasoning in the style of Lilo. So that's all I have for today. Artifact for this paper is available online on Zenodo, and we are also preparing a website and open packages. Thank you.
Questions?
Thanks for a great talk. You only showed the example of terminating programs and peripherals that do not really cover instructions that can loop. How do you handle non-termination? Do you use co-induction?
Oh, we're fully supporting. Oh, we are fully. Thank you for the great question. And oh, okay. So thank you for the great question. And CRIS is actually using interaction trees, and all the simulation rules are based on PACO and GPACO. Okay. So we can all support the non-terminations and conditions.
Okay.
More questions from the audience? All right, I have a question for you. What if the functions you try to inline is recursive? Would that be a problem?
Sorry, I didn't
what if the function, for example, in your example, if it's not a one-liner, but like the function body is a recursive call, some program and a recursive call to itself, would that be a problem when you're inline? Like, I imagine when you apply your proof rule, you would just like keep inlining again, right?
Oh, you mean the recursion, or? You mean something like recursively inlining?
Yeah. So for example, in your main function, you call the set function, and if the set function is a recursive function, would that be a problem?
Not in general, because as I said before, we have the co-induction principles to handle those kind of recursions. And inlining is not the only way to handle the function calls. We also have the other rules for the function calls. If it appears like identical on both sides, that's the another way to handle those kind of recursive calls.
We can have one quick question from the audience. All right, I have another quick question for you. Can you talk a little bit about the automation situation? Like, do you have any automation built in the framework?
Which kind of automation?
Automation, like, are the users supposed to manually apply those rules?
Oh,
and
yeah.
Manually do the refinement, or there's like?
So for the users in simulations, we provide like almost fully automated reasoning tactics for the users. If you are asking about the
tactics
generating the proof itself automatically, or the user for the user.
So for example, is it possible to just have a program and then you like a push button tactic that just like try to discharge everything?
Not yet, but the recent AI models are really good at it, and very fast. I mean, they are keep getting better very fast. So
I see. Thanks.
We hope to see that.